So now that we know that there are conservative forces and that there are dissipative forces, we can kind of classify these into different categories. So we first start off with conservative forces. Conservative forces are the typical ones you'll encounter in this class are first gravity for sure, and then the spring force. Those are ones that you certainly will encounter. Later on, there's the electric force. That I gotta spell right. But in general, there's any force as a function of position. I have X here, but might as well be vector R. And the implication about those forces is that the work done, so I'm going to switch to actual whiteboard pen. In all these instances, the work done by these conservative forces equal to the change in the potential energy of the system. It's always shared between two objects. The potential energy shared between in gravity is between the Earth and the block, or the mass and the spring, or the two electric charges, or whatever is going on in the situation. So that is that's the first example, the conservative force. And then the next one is you have dissipative forces. The classic examples of those are going to be kinetic friction and drag. Kinetic friction and drag. The implications of those two are that the work done by those dissipative forces is always expressed as a negative. It's less than zero, right? It's always less than zero, and it's expressed as the increase in thermal energy. I mentioned this last time, but now I'm really trying to hit home how all these forces are classified. Okay, so forces can be either conservative, at which point the work done is expressed as the change. Oh, there needs to be a minus sign up here. There needs to be a minus sign right there of the minus change of potential energy. And then the work done by the dissipative forces is minus the change in thermal energy. So the last one is just it's possible that there's forces that are neither of these. And those are forces that we're just going to call external forces. They're neither conservative nor dissipative. And these are the ones that might increase the speed, might decrease the speed, but the amount of work that they do will change on the situation. So these are like everything else: normal, tension, thrust, any like generic applied pushes and pulls. And so there's no real energy to consider in this case. They just do work. Okay? They just do work, and the work that they do in general is summarized by the work that the work that these external forces do is just expressed as a generic, perhaps integral, because it could be variable, along the direction of motion for simple one-dimensional problems. Okay, and so our general equation then, which we started off, of the energy of the system equaling the work done by external forces. Now we can break up the system into three different parts. Change in kinetic energy plus change in potential energy from conservative forces plus increased thermal energy from the external forces. Perhaps another way to say that, there's a higher level of that where we just say change in kinetic energy is total work, and then you can say that total work is work done by dissipative plus work done by conservative, I guess plus work done by external, and then make that connection on the left side, but not a big deal. And so what we do to make this really useful then is to break up the kinetic and initial into, or kinetic and potential into its initial and final. Leave this, there's never like initial and final thermal energy for these problems. It's always just change increased thermal. We say delta E, but it really is increased thermal. And so if we bring the initials to the right side and the finals on the left side, if we bring how about this, finals on the left, initials on the right, we end up with our general equation for conservation of energy, which is, that's the highlight of the chapter, K initial plus U initial plus any work done by external forces. That's going to equal K final plus U final plus any increased thermal energy. So that equation, I'm going to emphatically box it because that is our general, that's our general conservation of energy. And so this equation in a very real sense can be used to describe not only any problem or situation we've encountered up until this point, but more or less all of the other situations that you will encounter in physics. The only well, that's assuming that the energy is transferred only by mechanical means or perhaps electrical means. Okay, the only thing that's not included in here is a heat, because heat is another way to transfer energy into and out of a system by macroscopic temperature differences. But anytime there's not heat present, then any mechanical effects are summarized in these examples. And so it's kind of fun to go through and consider different situations in which some of these would be zero, some of them might be positive, some of them might be negative, and just to show different examples of them. So that's what I want to do next. A couple quick examples of, I'll save this actually. So, you know what, I'm gonna say that since we're almost out of time, that we're just gonna have to cut it short.